Hello everyone, welcome to Altair's virtual webinar series, Ask the Expert for Simulation Driven Design. Myself, Milan Raval, I'm an application specialist at Altair, and I'll be walking you through the topic of design a filling system of your die casting using flow analysis in InspireCast. So, first of all, before we start, let's talk about a quick intro of the InspireCast. InspireCast is fast, easy, accurate, and affordable framework tool for early casting feasibility and process development. Within the 5 easy step workflow, user can create runner gating systems for the geometries and optimize the casting process. InspireCast runs on finite element analysis, and user can take leverage of this tool to perform the casting simulation. Now, objective of this webinar will be setting up a model and running a baseline test for the die-cast component, analyzing results like flow pattern, air entrapment, filling results. And based on the previous run, we will perform the gate optimization and run another simulation. Analyzing these results, we'll do a runner creation within InspireCast, and then we'll run a final simulation with part and runner together. Now moving on to the InspireCast user interface. We'll perform the baseline run first with only part. Here I have imported the geometry for the diecast model in the InspireCast. I will rotate around a bit so you can take a look at how the part looks like. And let's start with setting up the model quickly. So first of all, I'll select the cast part icon. I will designate the material type, material group, and the temperature for this casting part. Next step is to define the gravity direction. After confirming the gravity direction, we'll create gates in some of the locations on the part. Now remember, we are trying to decide how we want to create the filling system or runner system. But initially, we are not aware of how we are going to or which location we are going to create. So first baseline test will perform with creating 3 random gate locations. Creating these 3 gate locations, we are also going to select compute flow tracing. That is a really good and new feature in InspireCast 2022 that will allow user to trace flow from the all 3 different gates. Next step, from the components, we are going to create steel H13 mold with 150 °C baseline setup. Then again, it is a baseline testing run, so we are going to use just a basic setup with initial velocity of 2.5 meter per second. Furthermore, we are going to decide the name of the simulation and will select the accurate meshing for this setup. Also in the analysis tab, we do not need to run solidification as we are only trying to simulate filling analysis and understand the flow behavior. They'll submit only filling analysis. Once the meshing and simulation is done, we'll take a look at the results. In the filling stage, our first priority is to take a look at the temperature flow. So we are going to animate these results and see how these 3 gates fill the cavity in terms of temperature flow. The next result we are going to take a look at is the flow front. How the flow front advances from all these 3 gates, how it merges together at some point, creates air entrapment in some locations. And based on these results, we'll decide whether we have to move our gate locations or not. Tracer ID, as I mentioned, we have computed the tracer ID for all these 3 gate locations that shows with compared to color contour that what and which region are being filled by particular gate that we have created on the part. Air entrapment result, as you can see on the screen, that shows the air is getting trapped in that location. All right, our next step will be running a simulation with optimized gates. So we'll start again with the part, and instead of creating random gates, based on our previous analysis, we'll create gate somewhere more relevant location. We'll set our part with the same material, temperature, and material group type. We have decided the gradient direction, and now we'll create gates into some location in the bottom. Our gates will be closer to each other, and instead of 3 gates, we are going to create 5 different gates close to each other. Remember, our goal for filling in this part is to create a homogeneous fill behavior. So optimizing these gates will perform another simulation, will analyze the flow behavior. Based on that, we'll decide whether we have to keep this optimized gate design or not. Gate size are 20 millimeter wide and 5 millimeter in thickness. Once the setup is done, again we'll use the same basic parameters and we'll create mold again with the same setup of steel H13 and 150 degrees Celsius. Basic setup with 2.5 meter per second of velocity, and we'll run the simulation with filling analysis type only. So this will be our another simulation with optimized gate design. All right, so once the result are there, once your simulation run is finished, we'll take a look at the results for our secondary simulation that we ran with optimized gates. First of all, we will analyze temperature in terms of the flow behavior. Now you can see clearly that with the optimized gate locations, flow looks pretty much homogeneous, right? The way flow advances at some portion, it creates a void as well. It creates air entrapment, but we'll figure out how to overcome that issue as well later on. Next result, we are going to analyze a stressor ID. For these 5 gate locations, we'll see 5 different color contour that shows how it merges together and fill the cavity in a particular pattern. Then air entrapment, you can see at the end of the part, we are seeing some air entrapment issues as well as where the flow front was merging together, creating void at some location inside the part. After this result analysis, our next goal is that we have decided this gate location looks fine. We are going to create a runner out of it. Now, InspireCast has capability of sketching and geometric creation capabilities and modification capabilities that will allow user to perform this kind of runner creation inside InspireCast. First of all, the previous run, I have saved that part and the gates as a parasolid and imported it again. So you can see I have my part and gates already allocated on the specific locations. Now, using the sketch tool, I can create additional geometries, can use geometric creation capabilities to create extrude out of this sketching, and then I can also use the revolve tool to revolve the surface. Moving forward to that, back and forth, creating sketch and creating extrude from the sketches, I can eventually get the runner design ready for my final simulation. So as you can see on your screen, just like a one gate that I have created initial filling system, similar thing I can do for other or rest of the 4 sections and merge them together into one location. I can use fillets from modification and create really smooth edges, curvatures on the filling system. And then in the center, where all five runners are going to connect together in one place, I'm going to create the short sleeve exit from where the material will be entering from short sleeve to runner system, and then from runner system to the part itself. So user can take advantage of sketching and geometry creation capability from Inspire Cast to create additional component or modify the existing. All right, so based on this example, I will quickly jump to our final geometry. Instead of doing this modification and geometry creation, we'll see our final geometry with all runners from the gate locations. So let's take a look at how the final geometry looks like with runner system and gate itself. So I'm going to import the finalized geometry that looks like this. So I'll rotate it around and you can see that I have created pretty good runner system based on the gate locations that we finalized, and also some of the modification of fillets of the surfaces and edges to make it more realistic. You can use your own expertise to make it more finer. Now next goal will be running part and runner final simulation. So we'll set up our model, select the cast part, select the material, temperature, then decide the gravity direction, also decide the filling system or designate filling system. And then here we are not going to create a gate, we are going to designate the surface from where the material will be entering the runner system. Then we are going to create the mold with the same material and temperature. And then instead of basic setup, here we are going to select advanced high pressure die casting system. But before that, what I'm going to do here is creating the components of overflow, because we noticed in previous run that there was some air entrapment. So on those two locations, I'm going to create overflows in which I can store the additional air that was getting trapped in those locations inside the overflow. And that way I can predict or create a simulation where part shows no air entrapment inside it. So with the pull down, I can select high pressure die casting, and now I have the phase change setup ready because I'm using a phase change point to transfer from initial velocity to second phase velocity. Initial velocity is zero point 0.5 meter per second that enters material from the circular surface, and then the white arrow shows that I have created that location. Once the flow front reaches that area, the velocity of the fluid will advance to second phase. Second phase velocity is again 2.5 meter per second. I'm going to run a simulation by changing a name, selecting the analysis type as a filling only, and a fine mesh. Once the run is finished, let's figure out how the result looks like. Alright, so these are the results that we are going to animate again. And initially, our first result is temperature. So we'll take a look at the how it fills the cavity, and you can see it is still homogeneous based on the run system that we have created and how the phase change point works. Let's take a look at the flow front, how it advances from each runner, merges together, moves forward homogeneously, and you can see the effect of overflow that is trapping the additional air. And then we'll take a look at the air entrapment result. We can see the air is getting trapped inside the overflow in both cases. So as you have seen in this 15 minutes webinar, that how we started from a single part where we didn't know where to define the gates, right? We started using a baseline test, then we optimized the gate locations, and then based on the gate location, we have created our final filling system. So now I will open this session for question and answer. Thank you for joining this webinar and listening to this session.